Let me get it in the presenter mode. All right, so hello everyone. My name is Omar Nofal. I'm gonna present a high resolution community level flood risk mitigation analysis approach. So I'm an assistant professor at the Department of Civil and Environmental Engineering at Florida International University. And actually this work was part of my PhD dissertation. I have been doing this work since 2017 to 2020. So it took me a while, but I'm gonna present it so that you can have an idea about the scope of this work. Just a brief introduction about the flood risk. Actually, I was giving this seminar as a part of my risk and reliability class. So it's the name of my class on the top. So for flood risk, usually when we talk about risk, it's a combination between hazard, exposure, and vulnerability. And usually sometimes there's misconception about the risk is just the hazard or the probability that you are exposed to the hazard. But here we are talking about a comprehensive definition of risk. So we are talking about your probability of getting damage from a specific hazard event to happen. So right now I'm going to present how to develop a high fidelity risk model with high resolution models of the hazard, the exposure, and the vulnerability of the buildings to flood hazards. So in the methods that we developed, we did kind of like different resolution analysis. So we did a staging and a resolution from like component level analysis to building level analysis to community level analysis. So the target resolution that we want to find, we need to make decisions at the community level, but at the same time, we don't want to lose very detailed information about the buildings and also the components. So we started to have detailed information about the component within each building, like what component types in each building, is there furniture, appliances, structural, non-structural components. What is the flood resistance of these components? Like what is the component elevation from the ground? What is the component replacement cost, so that we can do some loss analysis. Also, the different building types or the different building typologies within the community, including residential, commercial, social institutions within the community, have different component type within each building. So we needed detailed information about the buildings within the community, like the building value, the building type, the building occupancy, the building versus floor elevation, foundation type, construction material, all these informations we needed about the building so that we can do building level analysis. Also, we needed information about the community, such as the digital elevation map of the community, the land use, the soil, and lots of information about the community so that we can build a community model. So that's like say that we need different types of data at different resolutions, including component, building, and community level if we need to build a community level model. So, and this is how the staging and the resolution works. Like you have some components within each building, and you have building from 1 to up to n buildings. And then the community has all these buildings within one database. So this allows us, this kind of resolution allows us to have vulnerability models at the component level. So we were able to identify what is the probability of failure of a specific component within a building if they got hit with a specific flood intensity, for example, 1 meter. And knowing the failure probabilities of the components, we were able to identify the exceedance probability of a set of prescribed damage states for a specific building. For example, if we have a residential building, we were able to know what is the probability of this building having a slight damage state or a moderate or extensive damage or even a complete damage. And then we developed an approach to extend the developed method from the building method to identify the vulnerability of the community, which we are gonna show later in this seminar. Doing such a staging in the resolution from the component level to the building and the community level allows us to do some investigation of mitigation measures at these different resolutions. Like, for example, households during flooding, they do some mitigation measures, but nobody has investigated what is the impact of these mitigation measures on the total loss. Like, for example, if a household knows that there is a flood is coming in like a couple hours or 4 hours, and he starts to put some sandbags, having a pump or something, elevating the water sensitive components like the TVs, the electronics, the gadgets, And all the stuff, if it's got flooded, it's gonna be damaged. So all these can reduce the flood losses. So to capture these, we need a component level method that can capture how the mitigation measure at the component level is gonna affect the total losses at the building level and also the community level. Same approach, like in same way, we did also, we're able to investigate building level mitigation measures. Like, for example, if you have a flood barrier system around your building, how this is going to impact the building losses. If you were able, like if you did mitigation measures such as increasing the vertical floor elevation of the building, having water bumps, and also community level mitigation measures, including levee system, flood walls, a flood gate, retention systems, all these has been included in this study. So having such an approach allows us to expand the scale of our analysis. We were able to do detailed risk analysis at the component, building, and community level, and also do community resilience analysis, and also can can pave the way to do recovery analysis for the entire community. So for the risk analysis, when we talk about like hurricanes, we are talking about, we have multiple hazards, and one of them, which is the focus of this lecture, is the flooding. If we're talking about exposure, so we can study the exposure of buildings or networks, but we are focusing right now on buildings, including residential, commercial, and social institutions. And there is different way to quantify the vulnerability of these buildings, either using fragility functions or using loss functions. For resilience analysis, with the approach that we have used, we can investigate different resilience-informed decisions, either pre-disaster or post-disaster, at the short term or long term, even at the building level or at the community level. For recovery analysis, you can, with the approach that we develop, we can track the functionality of the built environment, what is in terms of social functionality and also the physical functionality of the entire community, and link multidisciplinary models in the physical models that we develop. Like if we know the damage, we can know how much economic disruption that we are going to have, and link this damage with some social models to identify the population dislocation and many resilience metrics we can measure using such models. We applied this to different hazard types. This includes the flood hazards and also multi-hazard hurricanes, like if the hazard is combined with wind, like what if we have wind and also storm surge and waves, how all these combinations gonna affect buildings. But right now we are focusing on flood risk analysis. So an example for the flood risk analysis, we used Lumberton, North Carolina. So Lumberton is a small city within Robeson County in North Carolina. We have detailed information about the buildings within Lumberton. So this includes actually the entire state of North Carolina have very detailed, and also one of the most detailed information about the buildings. They give you, for example, the roof type of each building and how many shingles on this building and how many nails in each panel. So it gives you very detailed information, including vertical floor elevation, construction material, foundation type, which is very important if you want to have a high resolution model at the building level. For the hazard model that we study for Lumberton, so for hazard modeling, we developed a high-resolution flood risk model that combined hydrologic modeling with hydrodynamic modeling. So hydrologic modeling was done using like a bunch of methods, which is a typical hydrologic modeling. They use detailed information about the rainfall, the land use, the soil, the digital elevation map, so that we can identify the water flow in each major stream in the study area. Once we identify this water flow, it's usually in terms of a hydrograph. This hydrograph is like how much is the water flow in each stream over time across the course of the whole flooding event. So as in any flooding event, you always have the water flow start slow and then it jump and then it goes slowly once the event is done. So the water flow peaks and then it goes back to normal. But the idea is not only to get water flow, we need to know what is the flood inundation across my study area. So we need to do hydrodynamic analysis to convert this water flow into a flood hazard map. So a hydrodynamic model was conducted, and then once we have the flood hazard map, we overlay it with a detailed community model to identify what buildings that are exposed to flooding and what is the level of exposure, like what is the flood hazard intensity at each building. Once we know the flood hazard intensity of each building, we use what is called the fragility curves to know what is the level of damage for each one of these buildings corresponding to each level of exposure. Like if you have a flood depth 2 meters, you will have this amount of damage. If you have 1 meter, you will have this amount of damage. So we applied this approach for the Lumberton, North Carolina, as I said, and we used Hurricane Matthew in 2016 as a hazard scenario. So Hurricane Matthew started as a Category 1 storm in the Caribbean and then intensified to be Cat 4, but at the landfall, it was a Category 1 storm. It made landfall on October 8th in 2016. And it was actually, there was a coastal flooding, but also there was riverine flooding comes from the heavy rainfall. So this is the one of the locations in the downtown Lumberton city. Shows how the flooding looked like across the city. Many businesses, residential building got flooded. And this map is from NOAA that shows how much is the hazard, the rainfall intensity across North Carolina, or across the United States, actually. The maximum was here, whereas Lumberton at, which is more than 10 inches of flooding. So for the hydrologic analysis for this study area, so we were able to get the flow hydrograph at the locations, or what we call is the upstream. So this shows how much is the flow and also the gauge height here at these locations. This is upstream of Lumber River, and this is downstream of Lumber River. So here's it shows how is the water flow jumped from 25 meter cube per second to almost 200. So it's like 8x like the normal flow, and also the same thing downstream from 50 meter cube per second to more than 400 meter cube per second of water. And we use this hydrographs as a boundary condition for hydrodynamic analysis. So basically we put this hydrographs here as a boundary condition and run a hydrodynamic analysis that solve the Saint-Venant flow equation, like a shallow water equation, to identify the water depths. And here's it shows one of the main locations. Like if you see here, you will find that we have a levee here that retains the water, but we have a weak spot here that allows the water to go inside the city. And on the left side, it shows where is actually this spot at, and it shows how's the water made it in the downstream. So this is one of the weakest spots that allows the water in. And this is one of the things that we are studying as a mitigation. What if we built a gate here, how much flood protection we can provide to the community? So after the flood hazard mapping, we mapped the flooding event after Hurricane Matthew, but also we did some return period events. So we studied what if we have a 10-year event. So here's it shows like there's minimum amount of flooding, just like the water flow in the river regions, and didn't make lots of flooding within the study area. But if we look at the 200-year event, which is like almost typical to Hurricane Matthew, so you will find that with a 200-year event, you will have much more overflow here within the south side of Lumberton community. So after modeling the hazard, the next step is to model the community. So to model the community, we need to have detailed information about the buildings, where they are, what is the building material, the number of story, occupancy, use, foundation type. We were able to have all this information. We collect some of this information from Google Street Map view, and also we're able to have this information as a GIS layer provided by the state of North Carolina. So using all this information about the buildings, we were able to categorize these buildings into archetypes. So we developed 15 building archetypes that can model the different building typologies within the community. 4 of these archetypes are residential, and some of these are commercial. Some of these are social institutions like hospitals, schools, 2-story and 1-story residential buildings, strip malls, shopping centers like Target and Walmart. warehouses. So we have these 15 building archetypes to represent most of these building typologies. So here's the name of these archetypes, like from F1 to F15, along with detailed description of each one of these archetypes. And then after we develop these archetypes, the next step is that we need to identify, based on each building information, what is the building archetype for each real building. So we have 15 building archetype and we have the real community. We need to assign these 15 archetype to the real community. So we developed a mapping algorithm that used the detailed information provided for the building and assign an archetype for each building. Like it's kind of like a Python code that makes some if statements. If this building is a 1-story on a crawl space foundation and it has this type of information, assign archetype 1. If it's 2-story, archetype 2. So it's kind of something like this. So on the left side we have the real community, and on the right side we have the mapped community. After that, so we applied this approach for many communities, applied this for Santa Clara County, California, Lumberton, North Carolina, Waveland, Mississippi, many states around the US. So here's it shows how's the mapping look like, so these are, all of them are buildings color coded based on their archetype. And once we map the community, the second step is that to overlay the hazard map that we developed with the community that we have and identify the hazard intensity at each one of these buildings. So here's it shows in 3D the hazard map overlaid with the community model that we developed. And based on this, we can do some spatial analysis to basically identify the hazard intensity at each one of these buildings. So right now we are done with the hazard modeling, exposure modeling. So the next step is, once we know the hazard intensity, how can we know the damage for each one of these buildings? For this, we developed a new approach for flood vulnerability modeling. So basically, for each one of the archetype, the 15 archetype that I showed to you, we divided the building into components, identified all the components within the building, and studied the flood susceptibility of each one of these components, including content, this furniture, appliances, structural components like drywalls, flooring, roofing, roof sheathing, isolation, all the component within the building. And then we developed the component-based approach that can tell us what is the probability of failure of each one of these components based on the susceptibility of each one of these components to water. So here's, for example, that shows, for example, the AC unit. So AC unit is is a water sensitive component. Once it got touched with water, it will be out of service. But the uncertainty is in the elevation of this component. So this component could be on the ground, could be elevated from the ground. So this picture actually from Lumberton, North Carolina, I take it myself. So some of the homeowners were smart enough and they learned it from previous events and they elevated the components that they have. So, but some didn't. So we identified an upper and lower bound of the elevation of these components. Same thing can be for a TV. TV could be on a table or can be mounted in a wall. The table can be 2 feet from the ground, mounted on a wall at 4 or 5 feet from the ground. So we developed we identified an upper and lower bound for the elevation of these components. And we developed the truncated normal distribution, and then we use Monte Carlo simulation to identify the failure probability of the component at different flood depths. So right now we identified the component vulnerability. What is the probability of failure for each component at different flood depths? But we need to move from component level to building level. So we developed this set of damage states. From damage state 0 to damage state 4. Damage state 0 is insignificant damage, then a slight, moderate, extensive, complete. And then let's assume that our building has 100 components. We divide these components into groups, and each group is assigned to a damage state. Based on the failure probability of each component in a group, we can know what is the exceedance probability of each one of these damage states. Here's, for example, shows some pictures of how we consider these damage state. Like if there is no water inside your building, so you are in damage state 0, but damage state 1 is 1 inch inside the building. So you have your carpet wet, maybe the flooring, is wet as well. So you'll have to replace the carpet with some, maybe the baseboard need to be replaced as well. Damage state 2, which include like from 1 to 2 feet of flooding inside your home. So maybe your appliances got damaged, your furniture, flooring, and drywall. And this is damage state 3. And also we have damage state 4, which is complete damage. This is an example like from the Excel sheet that we developed for the component that shows how we group the component, like from component 1 to 6 is damage state 0 here, and from component 7 to 13 is damage state 1, 14 to 37 is damage state 2, and we have also 3 and 4. And these some of the names of these components. Here's it shows how this thing is working. So as you can see here, we have a one figure that has maybe 100 fragility curve. So this 100 fragility curve is for the 100 components within the building. It tells me what is the probability of failure for each component within the building. And this was for 2-story residential building. And here I like color coded some of these components. So just like to highlight maybe 5 of them, including the AC unit, some drywalls, the cabinets, the flooring. And then we were able, through the grouping the components based on their contribution to each damage state, we were able to identify the exceedance probability of each damage state. It's kind of like you have 10 component contribute, for example, for damage state 3. So we make like a weighted average to merge these 10 fragility curves of the 10 components to be a one curve like this. Also, we applied same approach for this is a 1-story archetype. Here's it shows also detailed result. Like here's the component fragility curves. Here's some of the loss curves. So basically, if we know what is the failure probability of the component, we can know what is the loss for the component. Basically, you multiply the failure probability by the replacement cost of the component. For example, if you have a failure probability of your TV is 50% and the price of the TV is $1,000, you multiply 0.5 by 1,000, so the loss will be 500. It's kind of like probabilistic loss analysis. And here is the building fragility curves, which is derived from the components. And also we were able to capture the total loss for the building, like the loss curve for the building at each flood depths. So, and also we were able to compare this with what the current standards is using. So most of the current methods is using HAZUS stage damage functions. And we compared this with HAZUS and it shows a great match at some point. There is some mismatching and it has some reasons which explain it very well in some of the publications, because we basically use different approach. HAZUS assume that the building cannot get 100% damage because there will be always some components to salvage. But in our method, we assume there is a specific threshold of water if the component reach it, so we consider it as a total loss. So we made the building to reach 100% losses. Also, we extended this approach to be multivariate. So here we only capture the impact of flood depths. So we were able to capture the combined impact of flood depths and flood duration. So right now we are moving from fragility curves to fragility surfaces and from flood loss curve to flood loss surface. So we did the same thing, but we just like make the flood loss function to be as a function of flood depths and flood duration. Like what is the probability of failure of a specific component if it was exposed for a flood depth of 1 meter for a duration of 24 hours. So this were investigated as well. And here's it shows the fragility surface for damage state 0, 1, 2, 3, up to 4. And here we have the loss surface for a building, like if a building was hit by a flood 1.6 meter for a duration of 60 hours, how much loss as a percentage of the total building market value will be look like. And these 3 curves are where I plotted the loss curves on the top of the loss surface. So basically, when I did the single variable flood loss, I assumed that once the component is reached the damaging depths, so it will be out of service. So I didn't include the duration. But once I include the duration, So I can have, if I have less duration, so the losses will be less. But here's my curve. It shows what is the maximum flood loss will be look like. We applied this approach for the 15 building archetype, including this is a 2-story residential building on a crawl space foundation. This is 1-story residential building, a gas station, a shopping center like Walmart, a strip mall, and multi-business buildings. And as you can see, we modeled all the interior content. Like if we have like a shopping centers, we modeled the aisles, the fridges, and everything within the building, even office buildings, schools, hospitals, community centers. And we have these fragility functions. So here's it shows how is the exceedance probability of each damage state. Like we have damage state 1, 2, 3, up to 4. And each one of these curves represent a single archetype. This approach has been used by the Office of Management and Budget in the White House to account for the climate risk on the entire US. So this like was impactful to be used by the White House. So right now we developed a hazard model and we have an exposure model and we have a vulnerability model, and we still didn't do community level analysis. So what we did, we used all these 3 layers, the hazard maps that we have, along with the community that we developed and the vulnerability models that we have for each archetype. And then we developed the code to calculate the hazard intensity at each building and identify what building archetype it is, and then use the fragility function corresponding to this archetype and do building by building analysis to identify the damage state for each building. And once we are done, we keep looping one more time to get to the next building until we finish the damage analysis for the entire community. And here's it shows an example. Actually, this is downtown Lumberton. It shows the color-coded map for the building based on their damage state. Like building colored in blue have 0 damage, but building in red has like damage state 3, which extensive damage. But most of the buildings were like in damage state 2, which is like moderate damage. However, there's some is damage state 1 as well. With this, I'm moving from risk analysis to mitigation analysis. So let's see how this approach was impactful when we done mitigation analysis. So as I said at first, doing risk analysis at the component level allows us to investigate what if the household was able to elevate some of the components. Like if you have a couch and you put the couch on a higher elevation so that your couch doesn't get wet. If you cleared your entire first story from all the electronics, the gadget, the water sensitive component, and you put them in the second story, how much loss reduction you will have. If you were able to waterproof your building, like having a bladder dam or a sandbags around your building, or even used a water pump, how this is counted. So we developed a very like a long flow chart that shows how all these mitigation measures can be handled. So basically we read all the information about the buildings, about the mitigation measures, like if you are using a barrier, what is the barrier height? And if you are using a pump, how long is the pump is gonna work? So we included all of this and identify how much loss reduction that you are gonna have with all these mitigation measures. So basically, if you are using a flood barrier, so we modeled it as simple as that. So if you have a flood barrier like this, so this is the building without a flood barrier, and this is the same building with a flood barrier. So if the water depth is less than the barrier height, so the flood losses will be 0 because there's no water will make it to the building. But if the flood depth is more than the barrier height, so the water will overflow the barrier and the barrier will be useless, and you will jump back to your original loss function. So it's either 0 or you will jump back to the original loss curves. So if let's assume that we have a barrier height of 1 meter. So from 0 to 1, if the flood depth is from 0 to 1, you have no damage. But once the water exceeds the 1 meter, you will start jumping back to your original fragility function. So you will end up with having like damage state 2, because you take all the 1 meter once at a time, because all the barrier is gonna fail. Same thing, if you are using bumps, we were able also to model using bumps or using bumps along with barriers. And I'm like showing some pictures where household were able to have some barriers and have some bumps around to take the water from the property and put it behind the barrier. So for using water pumps, the 3D function, the 3D loss surface that we developed has the impact of flood duration. So as soon as you decrease the amount of water duration, you are using a completely different loss function. So if your flood stays for 6 days, so the flood loss curve will be this. But if you were able to decrease the flood duration to 1 day, so you will be able to use this flood loss flood loss curve. If you decided to use fragilities, also the fragility function in 1 day is different from 2 days, 6 days, 8 days, and 10 days. So it's basically, we cut sections in the surface so that we can get these fragility curves. Also, we studied the impact of elevating components. So basically, if you elevate the water sensitive components, so you will not be exposed to flooding at the original depths, like the TV was at the VersaFloor. So if the water reached maybe 1 meter, so the TV is gone. But if you elevate it to 3 meters to the second floor, so you save the TV. So here's it shows the blue line, the blue curve without any elevating components, and the red curve is if you elevated the water sensitive component. It's not that much saving, maybe around 10% saving, the maximum that you can save, but it adds up if you did it at the community level. However, at some point, if you elevate the component, it will be useless, because if you, for example, having a flood depth of 4 meters, and what you did is that you elevated, for example, a component that is exposed at 1 meter flood depths, and you put it at the 3 meter level. Once the flood hit the 4 meter, so this component is going to be flooded. So it's good at some point, but after that it will be useless. This is like shows the combined impact if you have a barrier, and also you are seeing what is the impact, the combined impact of using a barrier and a pump. So here it shows how is the loss curve for each one of these. Also, we investigated some community level mitigation measures, like what if you were able, for example, as I showed at first, this spot allows the water in the community. What if we block this spot? What if we build a floodgate or a temporary barrier at this location? How this is going to impact the amount of flood losses? What if we were able to enhance the levee system? What if we build a levee like this green line to protect this area, like this green line, and then allows like the water not to overflow and just flow in the river. And the same thing, what if we were able to build a retention system? This retention system can take the overflow from the river and store it in a retention system, and regulate the amount of flow in the river, so that we can, like when the peak is gone, so we can allow the water to get out of this retention system with a reduced flow. So we investigated all of this, and I'm gonna present just one scenarios. We did all the scenarios that I was talking about. So here's it shows one of the scenarios. If we built a floodgate and enhancing the levee system, it shows that we provided full protections for the buildings in the floodplain as shown here. All right, so with this, I'd like to thank you all for listening to my presentation, and I hope that you guys like understand the concept. I was like a little bit fast in some places, but if you have any questions, just reach out to me. And if you have any question right now, I'm ready to answer your questions.